Okay, in this segment, we'll introduce analysis of variance, or ANOVA, which stands for analysis of variance. One thing I want to emphasize here is that even though it says analysis of variance, we're looking at the differences between population means. So the purpose is we're going to look at groups, 3 or more groups, and what we want to know is that are there any statistically significant differences between the population means for those 3 or more groups. So for example, if we had 3 groups, A, B, and C, at this point we're just asking, is there at least one difference? It could be mu A different from mu B, mu A different from mu C, or mu B different from mu C. If that question is answered with a yes, then we'll go to the next step, which is which specific means differ from one another. So in part A, are any of them different? Mu A to B, mu A to mu C, mu B to mu C. If we answer that yes, then we come down here and we might say, well, the only one that's really different is mu B and mu C. The other ones, differences in the other ones could just be random error. They could all 3 be different from one another. It could be 2 of them, it could be any combination. But in the first step, any differences. Second step, which ones differ. Okay, again, we're analyzing variance, or analyzing variances, and we will focus on that sum. In other words, we're going to compute some variances. But it's important that you focus on the purpose, which is to examine whether or not there are differences between population means for 3 or more groups. It's easy to get lost in some of the arithmetic and lose sense of the purpose. We want to know if there are differences between population means. Now, I've been saying 3 or more, but technically you can use ANOVA for 2 or more. It turns out, and we've been using the independent samples t-test, and we'll continue to do so when there's 2 groups, and everyone does. But technically, you could just do what we're going to do, the one-way analysis of variance for just 2 groups, and you'd get the same answer as the t-test. And if you want to kind of get some sense of that, look at the second column in our t-table. Square those numbers, and you'll find out, go back and go over and look at the F table, which is we're going to use for ANOVA, and you'll see that the first column of those are equal to that second column of values squared. That's not that important to know. I just want to indicate that it could be used instead of the 2-sample test. More, what I really want to get at is that it's not that much different, at least in purpose, to what we've been doing up to this point. I want to give you in this introduction just a note about causation, mainly because people tend to associate analysis of variance with experiments and controlled experiments and causation. What I want to stress is that causation is mainly a matter of how you design the study, not the statistical technique that you use. Causation is warranted in a well-designed controlled experiment, the extreme and where you really would like to be. You can't always be where you'd like to be, as in a lab where you can control everything. At the other end of the spectrum, when you have strictly observational studies, this could be a survey, direct observation, or whatever. Anyway, you haven't done anything where you've randomly assigned people to do this training method or that training method or anything like that. You just maybe given them a survey and asked them how much training they had or what the quality of the training was or whatever. But causation isn't warranted in those observational studies. Of course, in between, and there are a lot of points in between, for example, in a field experiment and business, if you are going to do experiments, there's a good chance it's going to be a field experiment because you want to know the effect of a promotional campaign on sales. Well, you don't do that in a laboratory. You do it in test markets, and that's out in the field. So that's not exactly an experiment, so it's not as strong of causation, but it's probably the best you can do in that kind of thing. So there's going to be some trade-offs there. Well, anyway, as I said a moment ago, ANOVA is often associated with experimental studies, but that's really a matter of history more than anything else. Bottom line, ANOVA can be used for experimental or observational studies, for that matter. Regression analysis, which we've sort of done a little bit with already, that's just when we have correlation coefficients and then y equals a plus bx kind of things. Those are linear regression analysis. Well, anyway, those are often associated with observational studies, but those can also be used to analyze experiments. So the analysis, whether you use ANOVA or for regression, for example, really isn't the thing that affects whether or not you should make a causal statement. It's the design of the study. Experiments at one end, or well-designed controlled experiments at one end, and observational studies at the other. In the end, and it probably won't be very obvious, but it turns out that analysis of variance and regression turn out to be the same thing, or at least subsets of the same thing, something called the general linear model, or GLM.